All right, hello. We have a lot more people online, so be a good crowd there. I'm happy to introduce Dr. Tuff here. We all know him as our friendly neighborhood data scientist, as he likes to self-describe. And I think it's true. And he works in the Earth Labs Analytics Hub here at CU Boulder. And he has both a bachelor's and PhD from CU Boulder's Ecology and Evolutionary Biology Department. And then he left Boulder for a bit and worked for the Max Planck Institute for the Science of Human History, and then for McGill's Sustainable Systems Initiative. And he specializes in modeling movement and demographic data in human and biological systems. And he's also our resident expert in ChatGPT and AI systems. So with that, we're happy to welcome Ty.
Thank you, guys.
Thank you.
Thank you. Okay, today is like technical workshop day. So it's one of those situations where you've all been there before teaching. Where like I'm like 1 week ahead of you. But that's how exciting things are. I think you're gonna really dig it. So let's start though, just with a scoping question. You guys have done some of these tasks, but I just want you to give me an idea of what you think a fast time would be for doing these tasks. So here are the tasks. First, we download Sentinel-2 data for June and July of 2021 for the bounding box around Boulder. Downscale those to 10-meter resolution, mask out the clouds in the water, calculate NDVI then for each one of those days, and then get a median, and then create a plot. So if you already had this code written and you just hit run, what do you think is like a fast time to do all that? There's not a right answer.
Well, the download.
Yeah, okay. Yeah. So what do you think is like all of that? Day. Some people probably did their entire PhD. It took them 5 years to do this, but yeah, a day, an hour is probably a pretty good guess. Method we're going to talk about today, 28 seconds. That's all right. No, yeah, exactly. But okay, it's 28 seconds to do that. Just pretty crazy. How do we get there? I'm going to give you a couple slides of just a story, give us some context, and then we're just going to play with some code and see how things work, okay? So let's start it with GDAL. Eric has done this a lot. GDAL. It's so if you have pretty much done anything outside of ArcGIS, any open geospatial engineering at all, you have used GDAL. It is the fundamental package that actually is doing all of that underlying math. If you've done it in R, if you've done it in Python, if you've done it in QGIS, any one of those, you're actually just using GDAL. Now, the history of this has largely been, we as GIS engineers wanted bigger and bigger and bigger workstations, right? You want huge workstations because GDAL runs on your workstation. So you need to get all the data in there, use your workstation, translate everything into GDAL. It does all the heavy lifting. You have produced some GIS. There was a problem with this, okay? When my very first postdoc moved to WashU, started trying to use HPC, I go and try to load my very first bit of code, and it pops back and immediately says like, cannot load GDAL. Start talking with the guys that run the whole thing. Turns out GDAL is it's a Linux package, but it needs more numerals than the normal Linux package does. So you have to use an alternative numbers package on your Linux build. So this is why most of the time a standard Linux build doesn't have this built in. It's not ready to use GDAL because it's using this lightweight number system. So you have to go rebuild your entire Linux system to have the better number system that could support GDAL, which could support all the other stuff that you want to do. So for decades now, as we've been trying to do these things on HPCs, this has been a massive headache. You have to go and ask the HPC manager to go rebuild their entire Linux module so that it works with your stuff. You usually can't load it yourself. You have to go to the manager and have them manage it all the time. And it still had this problem of you're downloading everything, right? The managers were still really frustrated because the geospatial people wanted to clog up the HPCs with all of this data. So GDAL, which is the open source foundation, They moved the whole package to a new place and came up with this cloud optimized version. This is going to be one of our many examples of things Tyson Swetnam has been telling us. Every talk he's given since he joined ESOL has talked about cloud optimized TIFFs and COGS and arrow files and Parquet files, every single talk. So this is one of those, like, we've all been not paying attention to him, and now we're finally going to understand what Tyson was talking about and hopefully get this like big acceleration going forward. Okay, so again, here's the old way, the big old rat through a snake problem. You have to download the big chunk of data. So here we have GDAL powering R, Python, or QGIS. Your data set has to come in bulk down into one of those. You cut away all the stuff you don't want, and you're left with the good stuff, and you eventually make a plot out of that, right? The problem is this we have all lived through the problems associated with this, how hard it is to get that snake, that rat through the snake, or the egg through the snake, or whatever. Here's what the VIS does, is it means you can do those operations during the downloading of the data. They have actually taken GDAL and implemented it in the file system in the cloud. And this file system is called the VSI system. So you can look at lots of different data providers. They've converted to a VSI. VSI is part of GDAL. So they're actually taking GDAL, and the cloud providers are loading it on their systems. They're storing the data in the proper formats. And what it allows you to do is call all of those GDAL commands in route from the download. So none of that ever hits your RAM. So I want you to think of this as more of the grazing. So this was the title of the talk. So we're going to try to graze on data and not eat data, right? All right. Now, where does that leave us? So here's a bison grazing. The very first model I ever ran was for this modeling class, and it was about this bite mass model of grazers. Okay. So this model has 3 parameters: how big is your mouth, how fast do you chew, and how far of a distance is there between patches. So we got these data, we had this 3-parameter model, and we had to try to figure out which the values of those 3 parameters. And you find out pretty quickly that the optimal way to deal this is to take one bite and to have it all chewed as you're moving to the next patch. And by the time you hit the next patch, you've chewed it all up and you're ready for another bite. Okay. So you have how big is the mouth, how fast do you chew, and how spread out are those data. These are the parameters I want you to think about when you're thinking about data. How long should I stay on that data set? How much can I get out of there? And until I need to move on. Instead of thinking about how do we get little bits of data that we need, grab them and move on, and not try to download everything. Little ecological reference, optimal foraging theory. This just tells us how long we would want to stay at a patch before we move on. But essentially, it's like the longer you keep chewing on a data set, the less new inference you're going to get out of that thing, and the more you're going to quickly want to add on to that. So there already have been people who have made this foraging versus animal foraging versus information foraging analogy, saying, okay, in the wild, you're looking for food, and you're going to look for good food, and new good food is going to let out a new scent that draws you in. You're going to discover the same thing with data. You get into one data set, it's really working for you, you're getting a lot of inference, and then you decide, oh man, it's not answering this question, and you start getting the scent of another data set that might be able to come in and help you out a little bit. You start wanting to add to that. So when we start thinking about big harmonization projects, bringing lots of data together, right, that's where this using GDAL in this pipeline can be really helpful. Right? So this is a dramatization of how we usually do it. Instead of grazing, we usually download this big chunk of data and then try to dive in and get what's going on. Here's me on the first day of a new project. You have no idea what information is even in there. You just go to spend a whole week just downloading the bulk version of every single data set you think might go into your project. And so again, we're trying to get away from this. This is the way that we've always done it because the technology was set up that way. But instead, we want to try to be good grazers and just graze around. All right, so we're going to have to code. If you want to follow along on the ESOL's GitHub page, there's on the data library, on the very front page of the data library, is a document called Stack QMD. So this is the one I'm going to go through. If you want to follow along, you're welcome to do so, but you don't have to. Some things. All right, so first, how in the world would this work? Well, show you, where's that? This is a unexciting database of just different data sets, and they're all zipped up. So they all have code names. It's not a very pretty data set, but one of the data sets on here is, I'm going to show you an example of. Here we go. Sibeli is doing a new project on mangroves, so I decided to do start with a mangrove data set. This is the mangrove project. Let's see, global mangrove project. Here is the page for Google Earth Engine on how to pull these data really easily and sort of tell you a little bit about them. But essentially, these are just polygons where mangroves are. And these are stored in a database. So here is the link of the S3 bucket these things are sitting in, and they are each just zip files. So you can easily go and just download these in the normal way that you would download them. Here's what's so cool. This is all we add. So here I'm making a call, like a file call name, right? Like you would just be putting in the file path. I'm adding it together from a couple different things, but here I have just a file path like you would do routing to your own hard drive. But in the front, it has this VIS precursor. So VIS zip and VIS curl. And those are the magic words that let you just mount to this data set and not download anything. So when I put this data set, when I put this in, it creates a live link that I can then do operations on. And none of those are actualized until it gets to the very end. So here I've put in that, and that is like the data are there now. That's the equivalent to I have downloaded them and linked them already to my home folder. And then this is the alternative piping. You can do the percentage by percentage, or you can do, this is just the alternative, the more generic R piping. And then here I've turned it into a vector and I've filtered it spatially for India. So with those two things, so I can hit this. This will take a minute. The internet is not nearly as fast in Seek as it was at my house. So it goes a little slower, but I'll move on to the next one while that's thinking. But boom, that's all it is like, I have now just added that one little file type, and now I have GDAL doing these operations while it's bringing the data to me, and it delivers the data just that tiny little bit at the very end. So I open up my activity monitor here. Take a second to read everything. Right, I'm at 4 gigs before I've downloaded anything, so we'll keep watching that, but I think you're going to see that it just like stays exactly there. We add 0 to anything until you print a plot. If you actually print a plot, that's going onto RAM, so whatever the size of that final plot is pops up on your RAM drive, on your memory. But other than that, it's just chugging along. Okay, so here's a vector file. Vector files are a little easier. They're just read sort of like a normal file. So here I can just vectorize. You could do this with large CSVs, for example, like GBIF, right? 1 GBIF CSV is a terabyte. So you need at least a terabyte, bigger than a terabyte RAM to be able to download that thing and open it if you want. If you use this, you can go in and grab one cell from that thing. None of it ever touches your RAM, which is pretty amazing, right? Okay, so now let's move on to the, these are still thinking. This one takes a little bit longer than the raster ones, but okay. Here I just needed the shape. So in the initial question, I said a bounding box around Boulder. So how do we find good polygons? OpenStreetMap automatically uses this format. So here I am in OpenStreetMap, and I'm going to get a bounding box. And so the only thing that ever hits my RAM is just the answer to this question. I say, here's Boulder. I want it in a SF polygon format. It's going to give me that, just that polygon at the end. So here, I guess it's polygon rather than the bounding box. Then down here, these happen on my computer in real time because I've actually downloaded this. So once I've downloaded this polygon, it was actually like a multi-polygon object with some other things. And so I had to choose which one I wanted, transform it. Now, why am I doing two different transforms? Well, as you can imagine, all these people, we needed some type of standardization for people making calls into the cloud. So you're not allowed to call into the cloud with a bounding box in any projection. You have to be in WGS84. So you have to be in this 4326 to make your request, because all of their data is going to expect the request to come in that format. But then they give it back to you in a more local projection that here I didn't want to download that and reproject it. And so you're seeing a second projection to dealing with the retrieval. So here, this could probably be simplified if I knew the system better, but I'm making a request in one projection and I'm retrieving an answer in another projection. And so that's what I have two going on right here. Let's see if this was done up here yet. Still checking along. Okay, so I get just a polygon of Boulder. Down here, this is when I'm going to organize the available data. Okay, so here conceptually, we need to sort of get something. Need a marker real quick. All right, here's an important step. Go marker on there. Okay, so we have the data stored right here in its native resolution. And that is called our collection. Because there will likely be like hundreds, tens or hundreds or thousands of those things. And so when I'm looking right here, I am trying to build a collection. See at the bottom, I have the stack image collection. That's the thing I'm finally building. And that collection is going to be everything that I want to be drawing from. So here I have searched for Sentinel S2, Sentinel S2, and Clog. That is the cloud optimized GeoTIFF. That's the format that's so special that's linked to BSI that's allowing us to do that. So when we're searching here, we specifically want cogs. And so by getting all the Sentinel cogs, they're going to be set up the right way. I'm going to put in my bounding box, and remember my request has to be in that 4320 projection. So I have it in the 4320 as I make my request. And and I also give it my time window. So here I said June and July of 21. And it fetches all of those. And then I say, okay, build that into a collection. These are the different bands. So you have to explicitly say, give me these bands or don't give me these bands. It's going to try to not give you bands that you don't want. So I say for Sentinel, I want these bands, and it builds this collection. This is just a JSON file that they have built on their end that just says like a list of all the stuff that is in your search. So all we have is a list of stuff that's in our search, and that's our collection. The next thing we're going to do is build a viewing window. I'm making this a little offset so you can see it. But and the view window, it sets all the parameters for how I want the data to be delivered. So let's say the native resolution of the background is 100 meters. In my view window, I literally just set whatever I want. I set 1 meter. I set the extent So I make a bounding box. I say what extent I want, and I say what time window I want in my view window. That could be anything. And so this is really nice if you're harmonizing multiple data sets and say I want Sentinel and I want Landsat. I make a collection of Sentinel, I make a collection of Landsat, I use the same viewing window. It's just going to translate them both to the viewing window. So here you're seeing the collection build. Let me scroll down, and here you're seeing me build the view window. So here's that different projection, because I tried to get around this, but I just couldn't figure it out. But it seemed to want to return it in this projection, so I just went with it. Just went to its projection, try to forcing it instead of forcing it to do what I wanted to do. But presumably, you're supposed to be able to set that to whatever projection you want, and it'll reproject everything as part of the view window exchange. You say, so here I have dx, dy, which is saying how big I want the thing to be. You can also do, there's an alternative command tx and ty, which tells you how many times you want it divided, the extent. So you can either set the extent and say divide it 10 times, and it'll make the cells all whatever size you want, or you can say make the cells this size, and it'll add as many cells as it wants to, and it'll expand the extent out to make match out. So we have projection we want, how big we want our sizes, and then here is what we want our time resolution. So here is period of 1 day. So it's going to take whatever the raw form is, it's going to automatically aggregate that to this time period. Now the aggregation is going to be done, you can specify done by median, and the spatial one is done by average in this case, but you can specify exactly how it's doing that, how it's resizing. And then you set where your extent is, and that's it. That's your view window. So conceptually, we're back here. We have first made a collection, which is just a list of all of the data that matched your search criteria. And then we have a view window, which is the really specific format in which you want to receive those data. Stop the India one because it's going a lot longer than it should. 1 day. It will. So let me show you. So here is, I made a GIF. Oh, and so this is all of the raw shots of Boulder from Sentinel. So you're seeing some of them are half shots. This is with clouds removed. So some of them are blank spaces and stuff. So that's why I then did a median. And so I did the MDVI for every day, and you get these weird shots, and then you do the median over the 60-day window period, and that brings you. Yep, exactly. Sorry, this crashed on me for a second, so or it was just going slower than I wanted. Yeah, so you say, if you say aggregate time by median, then you give it whatever time window it wants, and it'll aggregate, it'll find the median at that time. You can say week or day or 10 days or 60 days. Or whatever. So let's skip the mangroves real quick. And got to. Okay, so I mean, that was really fast, right? We saw that in real time with my computer running at Zoom, and I could still do it that quickly, get that polygon layer. Here is in real time, we build our collection. So this is searching through the entire database, okay, and that was pretty quick. So here's what it's returned. We had 23 images with 12 bands each for that extent and for that time period. Here they are. These are the names of the actual files if you wanted to go find them yourself. And then for the bands, essentially how many, that we see bands for all of the images have all of the bands. Now here for our viewing cube, just because it's going a little slower, I'm gonna make this a little bit bigger. I'm gonna do 200 meter pixels. That's really fast because we're just reading in the view cube. It's not actually doing anything. Okay, and then here is where we actually call the thing. So raster cube, that is the R function for pulling all this together. It's going to pull that collection and it's going to pull the view box. So those are the two things that go into the raster cube, and it is going to make the digital object. So this is a virtual object that R thinks is real. So R thinks this is a data frame in its RAM, but in fact, it's just a network linked thing. Okay, and now here's the cool part. This is the really thing that this is the thing that really speeds things up. Is we're going to do all of these processes in route. So we've said, okay, here's this data set. It exists, it's here. And we're going to do all these piping processes, and you only give me the last thing. So first thing I'm going to do is select the bands. For each band, I'm going to take the median of each one of those bands across the time frame. Then I'm going to plot those. And so I hit this, and you can see down here at the bottom, this is what's happening on the cloud. So again, let me pull up my monitor. Our session, the RAM has gone down somehow based on what it was last time. CPUs, we have 4 cores going, sort of trying to exchange this information really fast. Nothing on the disk. And here's my network. Network's going a little crazy because it's sending information to me as fast as it can. But this is my download. That's the totality of my download. I downloaded the image at the end. I downloaded the plot. I did not download the Sentinel data. So, when I did this before, there was some latency on just the thing, and it didn't go all the way in, and then just popped up and was all done. Show you some other things while we're waiting for that. Yeah, guess I don't need to show you anything else. So this VSI system, I'll leave this up and just watch it. This VSI system can be used directly with S3 buckets. So if you have an Amazon S3 bucket, there's a particular VSI code, prefix that we use to link to your S3 buckets. You can do this to FTP servers if you want to go directly to an FTP server. Well, since we're going slow, let me. I'll open CFT real quick. We'll start playing with it. So that's checking along. Let me talk about CFT. So CFT is the Climate Futures Toolbox library that we built for all. Now this uses this logic. So that's why we started with this, is that CFT uses the same logic of trying to not download stuff unless you absolutely have to. So you're going to find the very first thing we do is just make a request to the server for the metadata. You say, what do you have? Let's look at the menu. So you're going to first request a menu, then we look at the menu of all the things you have, and then go try to just order the one thing on the menu. But that is the main logic behind the CFT package, and it matches the same logic behind the VSI system. It's that let's not download things. So if you go and you just sort of, you can now grab hundreds of things from the internet and have them all delivered to exactly how you want them. and have that be the only thing that you ever touch. All right. Keep an eye. Oh, looks like we're at 100%. Boom. Elapsed time was, yeah, 9 minutes. Well, actually, it only took 9 seconds to do the thing. It took 260 seconds to actually just download it because of the internet latency. So, but 9 seconds is how long it took to actually do the, and this I made in course resolution, so it was fast. Like, but still, I mean, just take a second to think about that, right? Like if you assigned a new graduate student the task of doing those things, it would take them certainly longer than 9 seconds. Probably take them like 9 months or something to even just figure out what to do. But it's pretty incredible, like how fast this can be. And all of it is not because you're shooting it through some fast computer. It's because you're just reducing the amount of the weight that you're lugging around with you. Okay. Now here, so this one up here, we were trying to do an RGB. So we needed the 3 bands of RGB, took a median between one of those, and so the plot was the median. The next one is actually calculating NDVI. So this is another thing, right? Like what we can add math, like we can add raster math to the call. Right here, it's just take these 2 layers and do this little thing and make this new NDVI column. But the idea that this could be unlimitedly complex. You could have an entire function in here, and it's going through and doing like pixel-based math on your entire raster stack in route to you. It's crazy. So here, I'll run this and we'll see. Again, it'll probably take 5 minutes or something, but because of the internet latency, but we'll talk about CFT while it's doing that. Okay, so back to CFT. We just have to do some normal library loading at the top. This is all just maintenance that you guys don't care about. Okay, so first, again, we need a bounding box, and the very first thing I go to is this get BB, which is part of the OpenStreetMap package. OpenStreetMap is just amazing at finding bounding boxes. So if you need to find a bounding box, you put in like a plain language descriptor of the area, and it's going to do a really good job anywhere in the world of giving you like a good bounding box for that area, and just like instantly, which is really nice. And what's so cool is that once you find that place that you like, you just ask for a polygon, and it will give you like a great polygon of that municipal area. So here's Lawrence, Kansas, again, just instantly, right? I didn't have to go to the Lawrence, Kansas website. I didn't have to find a data download repository, anything. Just ask for it by name, and it just shot it to me. So here, these are some OpenStreetMap commands that tell you sort of how you can pull in features from things. So in OpenStreetMap, I put that bounding box, and this is that link. This is the same thing that we were talking about before. This little OPQBB, this is making a virtual link to the OSM database for that bounding box. And your computer thinks that it's on RAM. It thinks it's already loaded in there. You can go do whatever you want to with it, and none of it is actualized until you get to the end of your pipe. So first, we're going to say, here's that digital link. Next, we're going to say, okay, give me some features from there. And I want any buildings that are a university. And then I want you to convert that to an SF object. And so when I run this, it's going to go, link, search, pull all those data. And while they're in route, it is, So here we got our return. It came up with some points, all the lines, and all the polygons, and all the multi-polygons that were returned. So we're gonna just select one of those for printing. All right, so let's move on. We don't care too much about finding buildings. Just an example there. Here again, this was all pulled from OpenStreetMap just instantly. Just saying like, make that link, say all the pipes that you want. It pulls it down and you only get the final thing. Python version of it. These I'm pulling rivers, I'm pulling streets, pulling everything from OpenStreetMap, and we finally make a big final map, and it looks amazing. But let's move on to Tuff. Okay. So CFT was set up specifically because the National Park Service was having, they wanted to do these big ensemble models where they compared different management plans across different places. So they needed the whole data set. So this was still difficult. They were spending like 6 or 8 days downloading the whole thing and having all these RAID servers in their room. And they just wanted to be able to speed that thing. So we made it much faster, but they still have this weird thing where they're still trying to get all of the data. So we're going to go through a quick example right at the beginning where we're just pulling, we're using that logic of just pulling a little bit of data that we need. And then we'll move up to what happens when you want to like get through all of it. So here, first, let's make our connection, our digital virtual connection, which should be running this first line. See at the bottom, it's saying attempting remote connection. Connection succeeded. And it'll do a couple more things. But now this word inputs is now our virtual link. That's now the thing that our computer thinks is a data set on the RAM. It's called inputs. And then we can go and do all these other operations to it. Now what you're seeing, so times, available times is going to be a metadata request for what times are available. Sorry, it's still connecting. It's probably fighting with the other one for internet connection. Oh, this one was done in DVI. Here it took less than 8 seconds, but again, it took 250 seconds to actually transmit it over the internet. And I made it really low resolution, but still, again, that's pretty amazing, I think. Let's come back over here. So it's taking longer than it should. All right, well, that's taking a little longer than it should, but let me explain some of these. So we first make the invisible connection. We search the metadata for what available times there are so we can get the window right. And then here it's going to look a lot like what you saw before, but here we have our connection. And then hyperfilter, these are ways, so this is a net CDF. So it's huge 3D like global client simulation of all of the air in the planet. And so it's just huge. So, but these hyperfilters are a way of filtering down that data to exactly what you want. It's a slightly different requesting system that we were doing before, but very similar. So we do first our bounding box and our time and our variable. So before in the stack call, those are the 3 things we said. So this is our bounding box. These are the data that we want, and the time that we want it. Connection has been established. To an R table. Yeah. Okay, so here we have those data downloaded. A lot of zeros. here's the timestamp, and there's a geometry to it. So again, this is precipitation. So this was saying there was no rain that day, or there's no rain projected that day. CFT looks 100 years into the future. You can switch and make it look 100 years in the past also, but this is a large global climate model, so it's not meant to be like super specific for a particular day, but it's meant to sort of project out for 100 years. So you see a lot of zeros in a lot of places when you look at precipitation data. And this shows just around Haskell where the data are spatially. So a lot of these data sets are spatially downscaled. So these climate models are run at like 2,000 meter spatial resolution. And these people downscale that with some physical models to say how it should be at something like 20 meter resolution. But then those downscale data are stacked out. So what I'm showing here are the exact points where each one of the data are actually stacked. And usually spatially, these are so huge, like even just one stack is like hundreds of gigs big, or can be hundreds of gigs big. So we were trying to go to individual points and download the entire stack, and even had to use parallelization for that. But the first idea is reduce the number of points to as few as possible. Maybe you need to do one, maybe you do three, maybe you do 10 if you want the whole stack. But you sort of have to think about, like, back to that grazing model, how big of a mouth do I have? How big of something can I bite? And that's going to determine how much you go get. Okay, and here, this little figure just shows that the center point of the Haskell polygon, this dot was the closest one to it. So that's the one that I picked. Just automated that process. And trying to wrap up here so you guys have time for questions if you want them. And here's sort of a big call of all of the, so that first one I called told me what my menu was, what things I could order. And now here I can go and I can say, okay, here's my input. Which things do I want? Oh, around on me, sorry. Here's that virtual link filter. I want all of the variables. So I named all the variables. It has two scenarios. I only put one of them. But here again, this is me filling out my menu order. I went and I saw what things are out there. I'm filling out a menu order and I'm putting it all on the order. And now it's going to give me just that as an output. So here are all the variables. Just made a list of everything that I wanted. And finally, we have this function called the single point fire hose. That's what I was getting to, where we had these specific users for the specific use of wanting to download that entire stack. And we want to use as much parallelization as we possibly could. So for this use, you go through and you pick one point that you want. You specify all of the things that you want, and then it just sort of blasts and tries to get all this data down to you. But this is a downloading method, which is the opposite of what we're talking about as a grazing method. All right. Let me stop all of that silliness and go back. I'll just leave it here. So this again is sort of the star of the show today, the GDAL virtual file system. This allows you to do that magic thing of making your computer think that the data set is already on your RAM drive and just being able to then do all these operations flowing towards you. That is the main lesson for today. So try to operationalize that, play around with it a little bit. The code is usually pretty simple. It's more just deciding what you want ahead of time and not sort of overwhelming the system. With that, I'll leave you guys 10 minutes for questions. Yeah. There is a server layer. This is why it's a cloud in the cloud optimized format, they're going to have it on a sort of an active server, and it's not just a flat thing. So that's what's doing all of that in route thing. Yeah. And so if you go into a lot of these services, they'll have like VSI as a standalone service. They'll have like a couple other access services, and then they'll add VSI on the end. But it's a nice way to steal a bunch of computation from the cloud providers. Like the Sentinel ones, they're coming from Planet. And so Planet's big resources. And I think for them, they're thinking it's actually using them less resources because everybody downloading the whole data set all the time is really clogs up their system. So if they have this functionality, it actually makes things easier, even if people are using all this computation to do the processing, because they're not using all the computation just to download the thing like all the time and repeatedly every time they need a new version of it. That's it. Make it fast. Yeah. I don't know. Well, no problem, guys. If you have questions, thanks. Yeah, and go try to make your code super fast.